right, so today we're going to talk about the standard C library, which is what you'll be using for your first program. So in any programming language, you have the core language, and then you have access to any libraries or packages that help you implement your program. So in C, there's the standard C library, and since you only know C, you won't know about the class libraries in Java or C++ or the packages in Python. But any language that you learn after C, you'll see that there's all this infrastructure code that you have access to, so you don't have to re-implement all of these functions. With the standard C library, if you want to use a function that's implemented in that library, you have to include the header file that function is sort of declared in. It's almost like declaring a variable before you use it. These header files declare your function prototypes for printf, for example. And then that lets the compiler know, oh, I know what the function prototype is, I'll leave a little stub there, and then when the program finally gets compiled and linked all the way in, I'll just make sure that actually points to real code. So that's what the header file is doing. And individual calls in the standard C library are implemented in different header files. And when you do a man, so the man pages, which I think is that part of the Bandit CTF? They already forced you to use the man pages. So when you do man on printf, right at the top of the man page it says, this is the header file that printf is defined in. And that's what you have to put at the top of your C program. Okay, so IO, time, string, math, these are all pieces of library code that are available to you. So yeah, man3 printf says, all the loops, C library calls are in section 3. And then in your Kernighan and Ritchie, they're also there. So we will get to this next week, but how you decide, so the standard C library is a blob of instructions on disk. One way to use that blob of bits is to say, as I'm compiling my program, I'm going to copy that blob of bits into my binary, and it's all there in one place. That's statically linked. Dynamically linked means that I'm going to just say, hey, at runtime, that blob of bits, I'm going to point you to that blob of bits in the file system, and then when you execute that program, I'll go to that blob of bits in the file system and then bring it in to execute. This will become really clear next week when we go through this all. Section 3. So there's 8 sections in the man pages, and 3 is reserved for printf, the C library calls. So when you do man printf, since printf, I believe, is only a standard C library call, it'll default to 3. But you'll see there are commands, and there are library calls that have the same name. So how do you figure out which one of those you want? Like, I think print is a command, and then print is also a call in a library. So when you do man print, well, which print did you want? Did you want the command, which is section 1, all the commands are there, or did you want the library call, which is section 3? So I forgot what all the other sections are, but I know 1 and 3. I don't know the rest, but that Google knows. So. All right, so the ones that we're interested in for this class, the classes of them, and we'll go through individually some of these. One set of standard C library calls deals with I/O. I/O to the screen, I/O to files, those sorts of things. Another class is the memory operations. So when you want to dynamically allocate memory to your program, those are the calls that you would use. Another set of library calls are for string operations. Common string operations such as find me the string length or compare two strings, these sorts of things. There are several utility functions. So the pseudo-random number generator has a set of calls, the rand and the srand, which is seeded to seed the random number generator. There are some functions related to timing, and so for your program, you're going to be doing a man of get time of day to figure out how you use that call and what parameters does it expect, what does it return you, how do you use the return value to actually get the wall clock time, those sorts of things. Later on in this class, we'll look at library calls that allow you to create new processes programmatically and execute new sort of binaries from your process. And then the final thing we'll cover are signals. How do processes communicate with each other? How do I send a signal to a different process that, hey, I'm done with my job and you need to do something for me. The other thing that is defined in the header files are implementation defined constants. We won't run into those too much. Okay, so I/O is the one you guys probably have seen a lot of. So printf, formatted printf, and string printf are the main ones. So I shouldn't say formatted, file printf, sorry. So they are all the same except for their destination. So printf by default will go to the screen. fprintf sends the output to a file, and we'll talk about what a file is later on. And then sprintf or sprintf just puts it to a string. And it does have a return value, which is basically the number of characters that it was able to print. Okay. On the other side, there are multiple scan input calls. So you have the scanf, which reads input from standard in. You have file scanf, and then you have string scanf to read input from either the file or a string that you pass it. And the return value here is the number of items that are assigned. And one of the things about scanf is that you have to give it an address, a pointer, to the location you want that data read into. And that means that that has to exist. You have to have allocated that in memory before you do a scanf onto that. Okay, so in order to do formatted input and output, you need to know about format strings, and those are the things that tell the compiler how it's going to interpret the variables that you're either going to send out to the output or interpret from the input. So if you're looking for a string, then it'll parse what you're inputting as a string. If you're looking for an integer, then it'll parse whatever you punch in as an integer, these sorts of things. So it just specifies the type of data that you're either spitting out or reading in. So you have the character, %C, the string %S, integer is %D, a long is %LD, so long double. And that's sort of the terminology. That's why %D is, technically that was considered a double word when this got defined, so that's why it's %D. And then you have %F for the floating points. Which ones were you guys using? Just %S, %D, those sorts? %C. Okay, so that's review. You've got them all. Okay, so here's an example. You have an integer x, and you say, hey, I want the user to give me an integer from standard in, which is just the keyboard. I'm going to scan it. So %D, I'm going to interpret it as an integer, and then I'm going to put the parsed contents, sort of the integer that I parse out of there, into x, the address of x. So address of x is now a pointer to x, and that's scanf will read that integer and put it in that variable. And then printf will turn around and print that as an integer, and that all works as you would expect. Okay, here's another piece of code. Let me see if I have my pointer. So just take a look at this code just to get you used to seeing this. I don't know how much programming you've done. So this, enter the first value, and then this does a scanf of an integer into that first variable a, and it checks the return value. Because if I scan and I say enter the first value and somebody punches in a bunch of letters, scanf is going to I didn't read a single integer out of there, and it'll say nothing. It'll give me a zero integers read. You should check that. That's how you error check whether or not you do some input validation, is what we call it. If you don't do that check, And if you don't get into the habit of doing that check, you'll get all sorts of errors and security bugs in your program. This can be pretty wordy if you do it everywhere, right? Everywhere where you have I/O, you have to do this. So sometimes you can, wrap a macro around this check, and I've seen where they map this into capital S scanf, and inside there they're doing the error checking, and then throwing you some exiting if you have issues. All right. So it reads one input, it reads the second input, it adds them, and then it prints it out. So that's an example program. Yeah. Yeah, in the shell, so unless you have told your shell to ignore errors and to ignore return codes, typically a shell will say exit status code 255 when you execute this and give it bogus bogus data. So typically you'd want the return 0, and it's like, oh, I'm good, that's a good code, success. But yeah, so then this means that, and these are implementation defined, what these codes mean, like for your program, so you can send back different codes for different kinds of errors if you wanted to. And that's the signaling mechanism. When we go to the end of the class, we'll say, we'll talk about, this is how you signal different conditions off of the error. Okay. All right. One of the things about printf and scanf is that you can supply them with format specifiers. So, for example, with printf, you can say, hey, I only want 10 characters out of this string. Like, I don't want usernames that are too long, so truncate that thing after 10 characters. If you got a floating point number, a real number, and you only want the width of that number to be 5 characters wide, and you only want 2 of those characters to be in the tenths and the hundredths places, then you'd say 5 total characters dot 2, which means a precision of 2 after the decimal point, and that's how you would format the output of a number. Another thing you can do is say for scanf, you can say %10s, and then this means accept no more than 10 characters, and then just truncate the rest of the input. All right. So, why do format specifiers matter? Oh, unlucky. This was not what I wanted you to see. Oh yeah, wait, this is what I wanted you to see. Look at this code. Does it matter that there's no format specifier there? And if so, what might you think happens? What would happen to this thing because there are no format specifiers? What would you imagine happening to this program? Yeah, what would you think would happen if you did a password longer than 9 characters?
Overwrite the previous variable.
Yeah, it might overwrite other stuff stored in memory. In fact, anything that's stored next to your password might get overwritten. What do you think might be next to your password in this program? Is administrator. That's my flag. So yeah, this is a doctored up program. But I have a flag here that says, yeah, this guy's an admin. And right now he's not. It's set to 0. But I'm going to have him enter his password. And maybe I'll flip that to 1 if his password matches. Or maybe the guy is going to, or gal, I should say, I don't want to be sexist with the hacking here. They could overwrite this password if you didn't say, hey, limit this password to 8 characters, actually, because there has to be a character for the null. Then I'm going to blast through here, and then maybe I'll hit that variable, because this variable is stored next to it. It looks like it. At least that's where you've declared it. And this is exactly what happens. So this is what you really want. You want to say there are 9 characters that have been allocated for the password. I need to make sure the string that I scan in has length 8 and then leave 1 character for the null. This doesn't have an issue with overflow. And so I will show you 2 programs and show you how this works. start this up. Bear with me. Let me pause the recording. Okay, so here we are. I'm going to show you this scanf. So here's the vulnerable version. And you see it's got the isAdmin is 0, the password, and I'm going to print the addresses of the password and the isAdmin variable, and you're going to see that they're close to each other. In fact, they're right next to each other. And then I'm going to say isAdmin, I'm going to print that out, and isAdmin will start at 0, obviously, because it was initialized to 0. And then I'm going to do the scanf, and it's going to print what the password and the isAdmin flag is after the scanf. And this will tell me whether or not that value got tampered with. And then if the isAdmin flag is set, I say, congratulations, you're an administrator. And so the idea here is that there is no place in this program where isAdmin gets set to anything other than 0. So this should always skip that printf. And so when you don't attach a format specifier to the scanf, then you have the ability to corrupt variables in someone's program. So let's compile this, and I'll talk about make at the end of this class. And so here is scanf. So the password is at this large string, but the ending is at 5D0, and this is 5E8, so they're fairly close in address space. So if I do a small number of characters, it works as intended. And then if I blow this thing up, and give it a whole bunch of characters, then you see it wipes out the isAdmin flag. So the isAdmin flag is no longer 0, and then it says, congratulations, you're an administrator. So this is why, at least with scanf, when you're scanning f strings in particular, you always have to put that specifier on there. Yeah.
You declare the isAdmin variable first, and then you declare passwords. Why is it that in the memory address that the isAdmin appears after?
So the C, I believe the C standard allows the compiler to choose where stuff is allocated, and so that's the ordering that's been given. Yeah.
But it's consistent every time, like arrays maybe are always first, possibly, or something.
It can vary. Yeah.
When I compile it, I get the reverse.
Yeah, so then this doesn't work. So you have to put the isAdmin on the other side of that. So yeah, that's why I didn't want to. I actually think that it does vary quite a bit by the compiler, how the compiler and what other variables are declared around it. Because sometimes the compiler's like, oh, I want to save some memory, or I want to pack this in a certain way, and it'll shuffle the order. So the C standard doesn't specify that the compiler has to allocate those in order. Yeah. All right. So you couldn't get those things to work.
And I just flipped them, and it's the same.
It's the same.
I'm running Ubuntu 16, the same thing.
Okay. One of the things, so the compiler is really good at catching errors like this. I had to turn some flags on in order to get this particular example to work. And this was just for show, mostly, just to demonstrate it quickly. All right. Actually, I think I have a different version of this that I would prefer to use. That's the one I want. Okay. All right, so is this code okay? So now I'm like, okay, use the format specifier. I got %8s in there. What's up with this code? What does it need? Does it need anything? Will it run? Get me what I want? All right, so what might happen if I actually ran this piece of code?
Chars are always supposed to be like 1 in general, right?
It's a character pointer.
Yeah.
And then I'm trying to, and character pointer is just how you read in strings.
It doesn't have any allocated
Yeah, it doesn't have any allocated
memory.
memory. So this, if CP is basically initialized to null because it's uninitialized, this will try and read my 8-character string into address 0. So this will give you a segmentation fault. So
you have to ensure memory has been allocated for anything that you read in. And I think this is the reason why I offer this up, is because a lot of times in this very first program, this happens to people, where they're trying to scanf into uninitialized memory, they're getting a segmentation fault, and they're like, I don't know what this is. This is what it is. So you have to make sure you have allocated an array that's big enough to store whatever string you're going to read in. And that's what this is. And then you can make sure that it doesn't overflow that memory. So here's a character array CP, and then you can treat CP as the address of CP of 0. So this ends up being a character pointer. And this is a pointer to the beginning of this array, and then it'll allow you to read the string into that array. All right. Okay, so there are multiple ways of doing I/O. That was the formatted I/O. You can do a direct input and output of raw binary data using these library calls: open, read, write, and close. And when you do an open, what open will return to you is an integer file descriptor, and that file descriptor is used on subsequent reads, writes, and closes to indicate which file I'm reading and writing to. Now in Unix and in Linux in general, everything is a file. And then you open and access files using these file descriptor integers. There are some default file descriptor integers on Linux and Unix that are defined. Standard input is always 0. Standard output is 1, and standard error is 2. So anytime you open up a program and you open a new file, the numbering starts at 3, because by default, writing to the 0, 1, or 2 is already taken care of. Okay, so one of the things that I think you might come across in Bandit is using these file descriptors in the shell. So when you're running a program in the shell, how do you get access to standard in, standard out, and standard error from within the shell? And Unix provides you these ways of manipulating these file descriptors. So for example, if you want to redirect standard out of one command to another, or to another file, then you can use this greater than sign or this pipe. So this is the pipe, this is the greater than sign. So the first example says, I want to redirect the output of ls into a file called outfile. And to do that, you'll use the greater than symbol to redirect standard out. Similarly, this command says, I want to take the input from infile and feed it into the execution of a.out. So I want standard in to be read from a file rather than the keyboard. And that's how you redirect that. You can individually redirect the standard out and the standard error. So we saw before, these both go to the display, actually. So any errors will go to, both the file descriptor 2 and file descriptor 1 will go to your display. In the shell, if you want those things to go into different places, you can use this greater than to the out file and then redirect the error file descriptor to error file. And it lets you split that off. What you'll often use in the shell is to pipe the output of one command into the input of another command. And that's what this vertical bar is. It's considered a pipe in the shell. And so you take the output of ls-l, and grep, or egrep, says, this is a regular expression search, grep for all the lines that contain tar. And it'll filter all the output and print out the lines that have tar in it. So if you have this, in fact, I think this might be one of the levels. If you have a directory that's filled with a bazillion files and you only want to find the files that have tar in it, that's the command you would use. Okay, and that's what you're doing. Okay, similar to the formatted input and output with printf and scanf, there is, and that goes to the standard file descriptors. If you want formatted input and output to actual files in the file system, not just to the keyboard and the display, you can use the file interface. And here you open a file and you get this file pointer handle as the return value. So in this case, I want to open /temp/x, and I want to have read permissions to it. And this gives me a file pointer. And then on that file pointer, I can do all sorts of fscan-fs, freads, fwrites, and those sorts of things on that file itself. So it's a more generic way of doing I/O to anything. Okay. So here's an example of using the file interface to do I/O to a file. So you declare your integer, a character pointer, and a file pointer. You set the file pointer to be the pointer that is returned from this fopen of temp file, and you say you want to have write access. And then I get this pointer, this character pointer p, and I point it to argv1. So it's pointing it to the very first argument. And then I'll do an fwrite of p for string length of p. This is the number of bytes that I want to write into this file. 1 is a number of times you want to repeat that write. So if I wanted the argument multiple times, I would put this as something other than 1. And then the file pointer. And then this will spit that argument into that file. So here's the output, fops hello, and then you cap temp file.text, and there it is, hello. So that's how you'll be doing file I/O. I'm not sure how much of it you'll be doing in this class. Did Bryant have you do I/O into the file system a lot, or? Okay.
We often type things.
Oh, okay. Oh, okay. And then which interface did you use? fopen? Okay. All right. So you've already seen this. All right. So strings. This is commonly used functions on strings, such as computing the length, copying, and concatenating strings. So if you recall, strings are basically an array of characters terminated by a null. Here are some examples of two strings that have been defined, name and title. And then they have the null at the end of each one. You can declare a pointer, p, and have it point to a constant character array. So this is a test. This is a constant string stored somewhere in memory that's immutable. This is a read-only string. So even though you have this pointer p that goes to it, you can't individually go and change the characters in this constant string array. And you'll find when you're doing your program, you might be trying to modify that string. Be aware is if you define this, the quick brown fox jumps over the lazy dog, as a constant string, you won't be able to manipulate that. If you want something you can manipulate, you have to do a string copy into a character array, like a malloc character array or an actual character array in your program before you can manipulate that.
Do all the regular string functions work on this pointer though, like string length?
Yeah, you can string copy as a source. So from this as a source, you just can't modify this because it's, and we'll see this next week. When the compiler sees this, it's going to treat this as a constant. And it's going to allocate space and read-only memory for this constant, and then it's not going to allow you to write it. In your program space, for example, your local variables, those are typically stored on the stack, and that's always readable and writable, and that's where you would manipulate the data directly. Okay, copying strings. So consider this code. P character pointer p is equal to all p's. Character pointer q is equal to all q's. P is equal to q. What does this do? Copy a bunch of q's into hex 100. So this is the address of p, hex 100. Address of q is hex 200. Does it copy all these q's into hex 100, or does it set p to 200? How many of you think it's number 1? How many of you think it's number 2? All right, it's number 2. Okay, so in order to copy strings, you have to manually copy it over, or you can use this string and copy to copy them. So with strings, when you are using the assignment and the equality operators, this is only looking at the addresses that the pointers have in them. So if you do p is equal to q, this is only true if those pointers are the same, have the same address in them. And then p equal q means that you're going to take the address that's contained in q and you're going to have p be the same one. Okay. So refresher. So here are some of the string calls that you'll probably use for your program. Length of the string, string length. Copying strings from the source to the destination. And a limit on the number that you copy over. So you always want to put a bound on the copy. A comparison. Again, this basically compares these two strings with a certain string length. And then concatenation, where you can concatenate two strings based on a certain number of integers. These calls deprecated the insecure versions which didn't have you specify the length. And very much like that scanf, you need the length specified. You needed the length specified for all these string operations. And the initial versions of C didn't have these implemented. And this is where we had a lot of the security problems in the 80s and the 90s, just because of these insecure APIs. All right. So you should never see these in code anywhere. And if you do, yeah, that code you shouldn't be using at all. Okay, so it is easy, even if, so we consider these API calls secure. Even if you're using these API calls, it still might not be secure. And so here is an example. So Charlie Miller, how many of you pay attention to the news with the Jeep Cherokee hack? So these guys figured out how to remotely hijack a Jeep Cherokee and get it to drive itself into a ditch. This was Charlie Miller was one of the two guys who was doing this work. So he gave this talk recently at an AppSec conference, and he showed this piece of code. And this is a piece of code that's checking the username and seeing if it's valid. And just by looking at this code, it's like, yeah, this has got a problem with it. So I want you to look at this code and see if you can spot the problem. So the first line, there's no problem in the first line. It says, hey, there's some crypto protocol to access the network and read in the username. So you want to secure the username on the network. So this is going to read this user buff into the bytes read. And so this is whatever the user input as his username. And then the logic of this program is to get the user length, do a string compare of that and all of the different names in a username table. And if it passes the check, it's going to say, oh, you're authorized. I'm going to prompt you for a password. Now, if you look at this logic, what could be a flaw? What would be the flaw that he saw in this code? Yeah, so if you look, the string length is based on the user buffer and not on the actual legitimate name that you're checking, right? So say you're going to check administrator, and the person types A. Yeah, so it's going to check the first character and be like, oh yeah, of course this is a valid user. A matches administrator, and then it goes and it prompts for the password. So that's a bug, but it doesn't necessarily make you administrator, right? Because this is just going to get you into the next part. So he coupled this with something I teach in web security. So here's the vulnerability, and it's good that you guys can sort of pick this out without seeing the punchline. There's another piece of code here, and you don't have the background to understand what this code does, but there's the way you store passwords in a database is through this structured query language. It's a database language. And as it turns out, you can inject SQL commands into it if the person hasn't sanitized the input properly. So you could be, the password field is trying to read in a password, but the bad guy can inject SQL statements into there. That's the vulnerability of SQL injection. So the first step is to bypass the username, and he bypasses the username by doing that trick. And then he bypasses the password by setting the password to this, which is saying, yeah, you're expecting just a password, but if I can escape out of the SQL statement, which is what the single quote is doing, I can just send you SQL, and I'm going to pass you or 1 equal 1, which is always true. It's the so that is how he completely owned. This is an Internet of Things device. So like Internet of Things devices they're just like this. They're all over, and they're very similarly coded. Well, I shouldn't make it a blanket statement, but a lot of them have these issues. And so this is what you're looking at with security. And this is why I put these examples straight up early, just so that you're aware of them. Yeah.
Why do they also have the security flaws? Are they just like they're made too fast, or like the Internet of Things just like
They're made too fast, and they're using programming languages that make it easy to generate these problems. And so as we go on in this course, I'll talk a little bit more about why C is a particularly difficult language to get right, program securely. There have been efforts to deploy other programming languages in which memory corruption errors are no longer possible, but shifting all of these developers from one programming language to another is going to be a hard thing. I might teach this class one day in something called Rust. I don't know if any of you are interested in programming a new programming language, but if you're a systems programmer and you want to do things a little bit more securely, that's a programming language that just got developed within the last 2 or 3 years. Oh, it's hard to program in, right? Yeah, so you get this trade-off. You could either program it securely or you could program it quickly. And so you have, in fact, you'll see this in web development all over. Like PHP was the first web development language, and it was really easy to generate web pages in it, but it was horribly insecure. And so you have this trade-off is everywhere. So, in fact, I refer to this as crap in a hurry, and I said, and I don't want to offend anyone, but like in the Western culture, it's the Starbucks effect, where we're in Portland, we like good coffee. Is that Starbucks? I'm sorry. I don't drink coffee anymore, so it doesn't matter to me. But like, yeah, you want your coffee quick, but you don't care if it's not the highest quality. That happens when we ship code all the time, right? You want it quick, functional, you want to grab market share, and then you want to worry about code quality. And that's the issue. And you see this with IoT, you see this with all of the products that get pushed out too quickly. So. All right, so where am I? Oh, I gave the punchline to that slide already. Hopefully you don't remember what it was. So one of the things, so another thing that you can make an error on is this stir and copy. Stir and copy does not guarantee null termination. People use this to say, oh, I'm copying a string. I should be copying that string's terminator, right? So if I, in this case, copy, say I have 2 strings, A and B, the quick brown fox, and then this substring, 0 through 8, and I do a string copy of B to A, string length of B, then shouldn't this now overwrite this and put a null there? It does not. Stir and copy does not null terminate. And this is a cause for a lot of errors too. So unless you know the API call and you actually read the man pages, which very few people do, you can get hit by this bug and not know why you've done it. So the output here, for those of you who didn't see what was on there before, what would the output of this be? You do this copy, and then you try and print A. Yeah, the numbers and then space brown fox is what will happen here, because it doesn't null terminate that. All right. So another common error that I'm hoping, so I've run this assignment 4 or 5 times,
And every time someone comes with me with one of these errors, I make sure to put it on this slide so that the next time people implement this, you don't see errors like this happening. All right. Other string functions, if you have a string and you want to convert it to an integer in your program, one thing you can do is the string scanf, and then say, hey, I want to parse this string as an integer or as a floating point or as a long word. The other way to do it is to do the string to L's or string to D's for the floating point and these sorts of things. So just a different API call for you to use for that kind of operation. I would recommend that you really use the string scanf, though. I think that's a better way to go. So here's an example. You have a string -23.5, and then you want to turn that into an integer. That's what you would use that call for, to interpret that string as a integer and set that integer value to it. Okay, so the next set of calls are the memory allocation and management calls. So the malloc dynamically allocates memory from the heap at runtime, and we'll talk about what the heap is next week. But this memory persists between function invocations. It's not like local variables, where local variables are stored, well, we'll see this, they'll store temporarily on the stack, and when your function is over, all of the local variables associated with that function are deallocated, are basically out of scope from your program. Malloc is different. This is like allocating a global piece of memory that's accessible from anywhere, as long as there's a pointer to it. So it allocates this memory block that persists, and it's important to note it's not zero filled. They won't initialize that block of memory for you. So here's an example of how you would use it. I have an integer pointer, I pointer. I am going to malloc the size of an integer, and then what malloc returns to you is an address, a pointer to that block of memory. I want to cast this to say this is going to be an integer pointer that I'm going to treat the return address of malloc from. You always have to cast it so that when you dereference this pointer, it knows that it needs to spit out an integer. So that's why you would put that decorator on there. Similarly, if you have a structure, and this is defined somewhere, and you have a pointer to that structure, or you've declared a pointer to a structure, you can malloc, so this should all be on one line, you could say, I want to malloc the size of that structure, and then cast that to a struct name pointer. That's how you would allocate them.
Can you explain why we should cast?
So this allows. So this decorator allows the compiler to take the bookkeeping. So when the compiler is using name pointer and someone dereferences it, it has to know exactly how much data it's working with. So the size and the attributes, it's generating code in your C code that will be able to access that. And that's why you have to declare its type. So malloc just gives you an array of, a flat array of characters, for example. And so you typically have to you typically want to declare the type of the return from malloc to be a specific type, so that when you are accessing that memory, it knows what object it is. So it might be redundant because you've already, so rather than saying, oh, I'm just going to infer it from the type of the pointer that you gave me, it wants you to actually declare it. So that's the reason why this might seem redundant, because you're decorating it on the malloc and then you're setting it to a name pointer, which is also one of those types. This is basically doing the declaration and the assignment all in one. All right, so is this code snippet okay? Copy string. You're given a string as a parameter, a buff, and you create a new character pointer, and you set this character pointer to be the malloc of the string length of buff times the string size of the character, which is 1 byte. And then you do a string copy of the buff, the input buff, into CP of the string length of buff. Is that okay? Yes?
No? If not, what would be the...
Are you missing the terminator?
You're missing the terminator. Right, so this string length is the number of characters that are in there, not including the null. So when you do a malloc of the string length of this buffer and the size of the character, you're not allocating space for that terminating null. And that's also an error that happens a lot. This off by one bug happens in C a lot. So you always should be in the habit of doing this if you're copying strings and you need to malloc space for that string. So you're mallocing the string length of the buff plus 1 to get that terminator in there. This is fine, whereas the other one isn't. And these are really subtle things that when we used to teach C, you wouldn't start off with this. But if you've seen enough problems in C, this is why you have to start out with this, because eventually this will get you, and it'll get you in a very subtle way. Okay, one of the things that C forces you to do is deallocate any memory that you've allocated. And if you fail to do so, you start leaking memory. So, for example, in your web server, Apache, if every time it serves a file, it leaks a little bit of memory, then eventually it's going to consume all of the memory in that machine and start swapping out to disk and having poor performance. And typically you want that web server up 24/7. So you want to get rid of all of the memory leaks in your long-running servers. And since most of these long-running servers are all written in C, this means that you have to be very careful with freeing all the memory that you allocate. And you can pretty much tell if you've got a leaky server is if you can just do a PS on it and see the memory usage of that thing just monotonically increase. And you know, in fact, browsers are great at this. If you have a browser and it's been sitting there for a while, and you sort of track its memory usage, yeah, there's some leaks in there. I think there are. So this is how you use free to free up any space that you have malloced. So if I've got this integer pointer and I malloc it and I cast it to an int star, then all I have to do is pass free a pointer to the memory location that I want to free up. And because it knows this type of pointer is an integer, it knows to deallocate exactly 4 bytes from the heap. Now, there are issues when you free an object, you have to make sure that it doesn't get freed again. If you have multiple pointers pointing to the same variable, so here's an I pointer pointing to this, say I have a stray pointer somewhere else that also points to that, and I free that pointer as well, then you've got a memory corruption error. And this is exploitable. So a lot of the double freeing errors can lead to someone to take over the process, the running process. So all these attacks on the heap are because bookkeeping on the heap is difficult. Another common security exploit is to use memory after it's been freed. Right? If you have a handle, so again, we'll take this 2 pointers case. You have a pointer to this memory block, or 2 pointers to this memory block. You use one of the pointers to free that memory block, and then all of a sudden you decide to use that memory from another pointer. That memory that you are pointing to is under the control of an adversary now. Because an adversary inside of the program could have allocated something right next to there and written whatever, maybe a bad URL or something in there, and then you have access to it if you used it after the initial free. So that's another memory bug. If you have a buffer overflow in the malloc, so we saw with the scanf, if I blew up that buffer, I could actually attack the thing next to it. If I have one of those in the heap, and I don't have an array here, but if I have one of those in the heap, then the heap data next to my entry gets corrupted, and I can do the same kinds of attacks with that. So all of these memory corruption errors are possible when you dynamically allocate memory. And this is why in the Power of 10 rules, they tell you, if you're going to use malloc, use it once, right up front, and then that's it. Don't use it inside your program just because of this kind of stuff. Okay. All right, I'm going to skip that. Okay, so you're going to need random numbers in your program. So the way it works is you have two calls. This is the first call that you would make, is to seed the random number generator. Say you want the rand function is deterministic based on the seed that you give it. So if you seed it with 0, it's a pseudo-random number generator, is what I should call it. It will give you the exact same sequence of random numbers. If you want it to start at a different sequence of random numbers, you would set the seed. So that's what I would recommend you do in your program. Set the seed for your random number generator first. You could set it to a truly random source, or it could be deterministic if you wish. But and then this is what you'll use the rand call to get the random numbers out of the generator. All right, so 2 parts. So here's an example of how you would use it in your code. I am going to seed the random number generator based on an argument passed to me by argv1. So I'm going to get argv1. It's a string. I'm going to do a string scanf on this string and parse those characters as an integer. And I'm going to read that into the address of seed. So this is an integer seed. I'm going to parse an integer. And then I'm going to call srand with that seed, and it'll seed that generator. And then I'm going to call it 10 times and print out the random number that I get out of it. And that's what you get here. And if you want a random number in a specific range, then you do the modulus. And in fact, you're going to probably do the modulus in order to restrict the range of your random number. All right. Is this straightforward, how you'd be able to use this in your program? All right, so that's the standard C library. Are there any questions? All right. Why don't we take a break? How about a 5-minute break, and then I'll start the next part.